one of the highest powered nuclear research reactors in the US, exists right here at MIT. So what's it like inside? Hi, I'm here for the tour.
Awesome, let's get you signed in. Take this.
What is this?
It's a dosimeter.
Oh, cool. Okay, thanks.
No problem. Sarah, they're all set. Hey.
Hey, Sarah. Wait, what's that? What's that?
Oh, that's my light that I turn on to let everybody know that I'm in the lab.
Oh, cool, okay.
So what you might not realize is that the reactor has very specialized parts, and if something breaks or something needs to be replaced as preventative maintenance, we can't just get a catalog and order a new part. We have to actually rebuild it from scratch. So this is why we need machine shops here on site.
So this is where you do that?
Yes.
Hi, PJ. Hi.
I got started when I was a freshman in undergrad. I was hired as a part-time student operator, and I stayed through all my years at MIT and through grad school at MIT, and now I work full-time here. All right, let's keep going.
Okay. Why is there this big, imposing door?
So the containment building is airtight, and this way any air that is going to leave the building goes past detectors and filters to make sure that we're not putting radioactive material into the atmosphere in Cambridge.
So right now, we are trapped.
No.
Okay, so this is where the power is made, right?
No, this is a research reactor. So we don't actually generate any electricity. We make lots of neutrons, which we use for experiments. And actually, we're the second highest power level research reactor on a university campus in the US.
Oh, cool. How come it's so noisy in here?
We have a lot of instrumentation running around us. We have some radiation detectors, so there's an air monitor here. And we also have an area monitor on the wall up there. And these help us to know what the radiation level is around us as we work. Because our body has no way of sensing radiation. It's not something that we can detect as human beings, so we have to have instrumentation to help us out.
How much is that? What does the 0.1 mean?
So it says 0.1 right now, and that's the reading in millirem per hour, which is a unit of radiation per unit time. And to put things in perspective, you get about 1 millirem per day living in Boston from background radiation from space and from granite rock in the ground.
Let me get this straight. We're standing 14 feet away from the core of a nuclear reactor, and the amount of radiation we're getting is the same as if we were standing on the street in Cambridge.
Correct.
How is that possible?
Concrete shielding, and I'll show you. So this is the outside of the shielding around the reactor core.
So this big cylinder of blue thing here?
Yeah, this light blue cylinder that you see here. And it's about 5.5 feet thick concrete shielding. That's heavy, dense concrete, so it's got metal punchings in it as well as sand and water that makes it better for absorbing radiation.
So it's not regular concrete?
Yeah, it's special concrete.
Nothing is regular in a nuclear reactor?
No. And that's where the nuclear reactions are taking place. So the fuel is loaded into the reactor core, and the uranium-235 atoms are splitting, which releases some neutrons, and those get absorbed by other uranium-235 atoms, which split and release more neutrons. So all the neutrons that we use come from the core here. Hey, Paul.
Hey, Sarah. So what's Paul doing, Sarah?
Paul's going to load some silicon into our silicon irradiation facility. So one of the things that we do here at the reactor is we irradiate silicon to be used as semiconductors. So silicon by itself is not a good conductor, but by irradiating it with neutrons in our reactor, we can change some of the silicon atoms to phosphorus atoms, which is called doping. So we dope the silicon material so that it has a distribution of impurities that cause it to become a semiconductor. So semiconductors can be used in all kinds of electronic applications, but the way that we irradiate silicon here means that we can be very precise. So the silicon that we produce here ends up in very critical applications such as airplanes and the power grid. Let's go see the reactor top.
Okay, let's go.
So this morning we're installing the new SALT experiment that we've been working on for several months. And this experiment will stay in the core for 1,000 hours to be irradiated by neutrons.
Let's go. This is the place where the tours normally stop,
Yes, that's right.
and you're gonna let me go past it.
Just you.
So what do I need to wear?
So I'll show you what to do.
Okay.
You need to grab some rubber booties and put them on your shoes.
Okay, now I step over here.
Yep.
Okay, and so my other shoe is still back here.
Yep.
And then I get the other one.
Yep. Anyone, they're not pairs. So we duct tape our pockets closed on the reactor top area because that way we can't be tempted to put objects in our pockets and then lean over the core and have them fall out.
So we don't want stuff to fall into the core.
No. It's very difficult to fish things out of the core and it could damage the fuel, which is a risk that we just don't want to take.
Has anything ever fallen into the core? Have you ever dropped anything in the core?
I've not dropped anything in the core. Do you mind if I put this on you?
Yeah, go for it. So, yeah, so can I take a peek in the core?
Yes, you can take a peek in the core.
Cutout on it, it should be closed when the grid is being closed.
The core is shaped like a hexagon, and it's made up of 27 diamond shapes that fit together to make a hexagon. And each of those diamond shapes is a fuel element. One of those diamonds is going to hold a cylinder, which we're using to hold a special salt that could be used in the future to cool down nuclear reactors. The reactor is a really good tool for testing materials because the core itself is an extremely harsh environment. There's very high levels of radiation, and we can heat the experiment to really high temperatures to really stress test the material.
So we're standing 5 feet away from an open nuclear reactor core. How are we not dead?
So in the core tank we have 10 feet of water between the top of the fuel and the top of the water level. And the purpose that that serves is to shield us from radiation when we're working in the core, and it also serves as a reservoir for cooling.
So 10 feet of water is enough to get the dose from thousands of rem per second to 10 millirems per hour?
Yep,
That's kind of insane.
it's amazing.
Why is water so good?
Water's really good at absorbing neutrons.
Success. Guess we're ready for the next step.
So the first thing we do is take our gloves off and in the trash.
Can you help me?
Yeah. So this is one of our neutron beams that you can use to do experiments outside the reactor. So the neutrons come from the reactor along this beam line, and you place your experiment sample on the beam line and detectors, and you can do the experiment here. So right now Gordon's explaining to his students how they're going to use the neutron beam for their lab class, for their experiment. And so the students can set up their experiment here on the beam line, and then they can collect the data that they need completely remotely from their dorm room.
So students at MIT can actually do experiments at the reactor?
Yeah. We have a lot of student participation here at the reactor.
So what kind of experiments do students do with the neutron beam?
So you can calculate the reactor's power level based on the speed that the neutrons are traveling. You can figure out how good a material is at absorbing neutrons, and you can also figure out the shape of molecules based on the way neutrons bounce off them.
Hey, that's pretty awesome.
All right, next. So this is Mike, and he's one of the experimenters working in the hot box.
Hey, Mike. Hi. What you working on?
So what we're doing here is we're disassembling experiments that have been in the core of the reactor in this shielded box. So the hot box is useful for storing and handling materials that have come out of the reactor. They need to go in here because they're too radioactive to handle close up, but we can handle them inside here because of the lead shielding in the walls here.
How much radiation are we talking here?
So the radiation levels inside the hot box are about 30,000 times higher than they are out here. And so that's why we have samples and the materials that we've taken out of the reactor inside here. But we can work on them safely using these manipulators.
So what's that sample?
The sample I've got there is a piece of silicon carbide with a chromium layer on the inside. And it's a potential replacement for current reactor cladding. And so we're testing it to see how well it does under radiation and temperature and conditions typical for a power reactor.
I have a question for you.
Sure.
Can I try?
Yes, you can.
Wait, really?
Oh, of course.
I never get to do this. What is this?
Actually, you know, we've got a little poly vial in there. Sometimes the trickiest thing is closing the lids on the vials.
Cool, thanks, Mike. See ya. Hey, Tom.
Hey, Sarah.
Tom's making gold radioactive for medicine.
Wait, what?
So we were actually going to be taking some gold pellets and using a rabbit, insert them into the reactor into an area with a lot of neutrons. And the neutrons will make the gold radioactive. So when the sample comes out, we can then ship it to a hospital where they can eject them into a tumor in order to cause radiation damage directly to that tumor.
So, wait, what about rabbits?
So they're not real rabbits. We have these poly sample holders where we put the gold directly into.
So you put the gold in the rabbit and then...
So the rabbit would go from where we inserted it through this tube and into the reactor. And then when it's finished, it will come down the tube and out into our shielded hot cell. So when the material's radioactive, the radiation is all contained inside of our shielded area to work with.
Okay, see you, Tom. Let's go to the next stop.
Okay.
So we're about to enter the control room, and the control panel is on the right, so please try to keep on the left.
So I shouldn't push any buttons, right?
No. Hey, guys. So this is the control room, and the most important thing in the control room is the operator, who is Sarah right now. Sarah is actually a student operator, and Paul is the shift supervisor currently. So right now they're working on the startup checklist to start the reactor back up.
Cool. Weren't you doing something with silicon earlier?
I was indeed.
But you finished,
I finished that.
and now you're here.
Correct.
Isn't it weird how one person can move from one place to another? Do you have a favorite button?
Yes.
Which
Wow, that's a good question.
This is the major scram button, which I've only ever pressed during testing. Never actually had to major scram. It's one of our emergency shutdown buttons, and it automatically drops all the control blades in, and it isolates our ventilation in case something were to get out. But I just like it because it's the big stereotypical red button in the reactor.
Do you know what every single one of all of these buttons do?
Yes. Some of the experimental ones, I wasn't covered in my training because I don't have to run the experiments, but all of the regular operations buttons.
What is high temp D2O reflector cleanup system?
So the reflector system with heavy water has a cleanup loop where it flows through an ion column, and if the water gets above 50 degrees, it could potentially damage the resin in the ion column, so that alarm will go off to tell you that you need to cool it down or you need to bypass it.
What does DP3 30 PSIG mean?
So that's one of our pressure gauges for our heavy water system. That's what the D means. That tells you reflector system, the P is pressure, and then 3 is just the number demarcating it.
What's this gauge do?
This is for auto control. So using this gauge here, you can set your auto control to tell the reactor this is the power I want to stay at. And this gives you the percent deviation. So if you're too high or low, that needle will tell you. You want to keep it at 0.
What's this knob?
So we have 6 different shim blades, and you can only move one at a time. So this is to select which one you want. So right now 3 is selected,
Okay.
but you can turn it and you can pick a different blade, just whichever one you want to move.
What is this?
This is the official console clock.
So you're a student, you said?
I am a student.
Okay, what year are you?
I am a sophomore.
So you're a sophomore at MIT,
Yes.
and you are running a nuclear reactor.
Yes.
That's pretty freaking awesome. Okay, so what kind of training do you have to go through to be able to sit at this console?
So there's a lot of studying through systems manuals, technical specifications, all the alarms and procedures, and then there's hands-on training where you come and you sit training watches and you'll perform practice startups supervised by your training supervisor.
Okay, so you passed my test, but please tell me there's a legit test you also have to pass, right?
They fly in an examiner who's an examiner from the NRC, and she'll come and she will watch me do a startup and a shutdown. I'll give her a tour around the facility, and she'll ask me a bunch of different questions about all our systems, and then she'll give me a written exam that covers safety procedures, radiation protection, reactor physics, things like that. So you have to be prepared in all areas of your training for the exam.
So did you pass?
So I have passed the exam, which means I'm licensed by the government to be able to take shifts and be on console by myself. To start up the reactor, you still need your supervisor in the control room with you, but I can perform all the operation duties in here alone.
All right, thanks guys. See you.
This is looking for contamination that someone may have gotten while working in containment.
And what happens if it's not clean? Like, what do you do if it says dirty?
Well, first it'll tell you where.
Oh, okay.
So that helps, right? If it's your left toe or your right hand. It's usually pretty low level, so to get the contamination off, think of it like dust. And so we'll use tape. We'll have light hand washing. And usually it's as simple as something on a lab coat cuff, say, that somebody has been working with a contaminated sample. And we'll just take that lab coat and put it in our laundry facility and get it clean.
This looks like, you know that thing from the movie Interstellar?
Yes,
You know,
I love Interstellar.
Yeah. What's
TARS.
TARS.
Yeah.
That looks like TARS.
5, 4, 3, 2, 1. Clean. Thank you.
Shall we go?
Yeah, let's go.
So these are both backups if that monitor were to malfunction.
See ya.
See ya. Okay,
Right.
thanks for the tour, Sarah.
No worries. There's one more thing we have to do though. I have to get your dosimeter back.
Oh, right, yes. There you go.
Thank you. So it's reading still the same.
So, okay, so wait a second. We just spent all day inside a nuclear reactor, and the radiation dose has not changed at all?
Correct.
Amazing.
Thanks for coming.
Thanks for having us.
Come back anytime.
Thanks.